Hey, welcome to Unit 2, Matter and Energy. Today's topic is 2.01, Properties and Changes of Matter. Now, here's the thing about chemistry. There are three parts to the definition of chemistry. Chemistry isn't just the science of stuff that blows up, although that's definitely part of it. Chemistry is the study of matter. We're going to define matter today. What is it, and how do you classify it into elements, compounds, and mixtures? The changes matter undergoes, and there's physical and chemical changes. We'll be looking at that in this video as well. And the energy associated with those changes. We'll be looking at that in a future video. This is kind of a microcosm of everything you're going to do for the rest of this year. There are certain subjects like chemical changes. There's an entire unit on reactions we'll be doing. Physical changes, there'll be units on solutions that we'll be doing, phases of matter and phase changes. Other chemical changes would include acids and bases and electrochemistry. So you're going to be just taking the broad view of chemistry today, and we'll drill down deeper as we go on in the course. You're going to have an entire unit on nothing but energy, but we're just going to introduce it in this unit. And of course, how is energy converted from one form to another? There's something you're going to look at called the laws of conservation that say that you cannot create or destroy energy, matter, or charge. You can only convert them from one form to another. So let's have a look at this matter. This diagram, if you're in my class, is on page 2 of your notes packet for Unit 2. And if you don't have my notes packet, well, the diagram's right here. Now, if you take a look, we have matter, which is anything that has mass or volume. And you can divide it into two basic categories, pure substances and mixtures. Pure substances are homogeneous. They're the same throughout, whereas mixtures can be homogeneous or heterogeneous. Substances fall into two categories. Ones that cannot be decomposed any further by chemical change, we call these elements. And substances that can be decomposed by chemical change, we call these compounds. Drilling deeper on elements, elements are made of atoms. In the middle of every atom, you will find a nucleus containing positive protons and neutral neutrons. Outside the nucleus, you'll find energy levels containing negative electrons. More about that in the next two units, units 3 and 4. No, 4 and 5. 4 and 5, yeah. If you can decompose a substance, then it's a compound, and there are two basic kinds of compounds. If the compound is made of a metal and a nonmetal, you'll be doing a unit on periodic table later in the year. It's an ionic compound. And if the compound is made of nonmetallic elements only, it's molecular. If a substance can be decomposed by physical change, in other words, without changing the chemical substances that it contains, then it's a mixture. Mixtures can be homogeneous, which are even consistency throughout. If you have a mixture that's stuff dissolved in water, we call that an aqueous solution. If we're dissolving it in alcohol, we call it a tincture. If we're dissolving it in mercury, we call it an amalgam. And if we dissolve metals into each other, we call that an alloy. Heterogeneous mixtures are ones that are not evenly mixed throughout. For example, a bowl filled with Legos. You can go through and every single fistful you pull out of that bowl will be different. A translucent mixture is called a colloid. An opaque mixture is called a suspension. So, with that in mind, let's move on. The universe, which is rather large, is made up of the following materials. We have matter, which is anything that exists with measurable mass and volume. Your room, for example. Energy is anything that exists that can impart force between particles of matter. For example, making matter able to move from one place to another. This is the power of electrons moving hair as far apart as possible because the individual hairs are charged negative. And there is also dark matter and dark energy. We're still not 100% sure about either of those yet, so we're not going to really discuss it any further. Now, types of matter. Like we said, there are substances which are homogeneous. They're what everything is made out of. These would be a representation of atoms of gold. You can see the homogeneous composition because no matter where you take your sample from, here or here or here, the composition will be identical because all you have is one kind of atom or possibly one kind of molecule. An element is the simplest form of matter that cannot be decomposed without losing its properties. And all atoms of elements contain the same atomic number if the atoms are the same element. For example, all atoms of iron will have an atomic number of 26, and all atoms of phosphorus will have an atomic number of 15. These elements down here have been given names above and beyond what are given on your New York State reference table. What all this stuff means we'll be dealing with later in the year. For example, when we do nuclear reactions, we'll be looking at the mass number and the atomic number. When we do electron configuration, we'll be doing electron configuration. And when we look at how atoms come together to form compounds, we'll be dealing with these oxidation states. This right here is an actual microscopic view of silicon using a gadget called a scanning tunneling electron microscope. More about that in the electrons unit. Okay, compounds are two or more elements that are chemically bonded, either covalently or ionically, or compounds cannot be made of metals only mixtures, because metals do not bond to each other in a definite whole number ratio. In a compound, the two or more elements must be bonded in a definite ratio. For example, calcium chloride is CaCl2, and it's always CaCl2, one calcium ion and two chloride ions. You can decompose compounds into elements by either adding enough heat or by adding electricity, which we'll be looking at in the second to last unit of the year, a process called electrolysis. This is sodium chloride, where we have purple sodium ions and green chloride ions, and with enough heat, we can actually separate these ions out and decompose it into its original elements. Next up, element symbols. If we look at the periodic table, what rules are used to make the symbols? Well, you'll notice that every element starts with a capital letter. If it only has one letter, then it is a capital letter. If there are two letters, then the first one is capital and the second is lowercase. And for the elements on the bottom, where these elements have not been given their trivial names on this periodic table, we use one capital and two lowercase levels. Untrium means 113ium. Unquadium is 114ium. Unpentium is 115ium. But these have already been given systematic names. They're just not appearing on this particular reference table. So if you have two capital letters next to each other, then you know what you have is not an element, but rather a compound. For example, capital C, lowercase l, that's not an I. You may make that mistake many times this year before you figure that out. This is not carbon and iodine. This is elemental chlorine. The C, capital C, lowercase l. That's chlorine. Whereas uppercase C, lowercase o is elemental cobalt. But if we have capital C and capital O, that's a compound. That's made of carbon and oxygen. It's called carbon monoxide. So if you can't break it down into simpler substances, it's an element. If you can break it down into simpler substances, then it is a compound. Mixtures are two or more elements or compounds that are not chemically combined in a definite ratio. They're just mixed together. This right here would be a pure sample of one element, hydrogen, for example. That would be a substance. This right here, all the particles are made of the same substance. There's one sodium ion and one chloride ion. This is hydrogen chloride. Again, a substance, a compound. But what if you have multiple substances mixed together, but they're not actually chemically bonded to each other? Well, in that case, we have a mixture. In this case, argon and hydrogen chloride. And in this case, we have argon and hydrogen. So you can have mixtures containing elements and compounds, two elements, or even two compounds, but they cannot exist in any definite whole number ratio. In other words, if I removed this molecule of hydrogen, it would still be the same mixture. So the composition can vary. If I remove one of these atoms of hydrogen, then it would no longer be the same substance. Solutions are homogeneous mixtures, which means that they are uniformly composed right down to the molecular level, made of a solute dissolved into a solvent. We'll be looking at that in a whole unit on solutions later in the year. If the solvent is water, for example, if we take these ions of sodium and chloride and surround them with water molecules to keep them apart, we have what's called an aqueous solution. Some things don't dissolve in water. For example, iodine does not dissolve in water. However, it does dissolve in alcohol. That would be called a tincture. A tincture of iodine, that orange stuff that you put on your cuts and then scream in agony because it hurts so bad. If your solvent is liquid mercury, you can bond all kinds of metals together in an alloy. Actually, this is not an alloy. This is, since it's mercury, we call it an amalgam. Amalgams can consist of many different metals suspended in mercury, and the result is actually solid. And you may have seen this in your parents if they still have their cavities. This right here is an amalgam. They don't use amalgams much anymore. Mostly what they use now is porcelain fillings because they blend in with the rest of the tooth. But when I was a kid, oh yeah, everybody's mouth was filled with amalgam. And if you have a mixture of two metals, and again, they do not have to be in any kind of definite proportion. For example, if we take these two metals and mix them together, we make an alloy. In this case, we've got copper and zinc just mixed together, and it gives you brass. Copper is very pretty and very shapeable, but also can be bent out of shape very easily. So if you want to make an instrument, you want to make sure you use something nice and shiny like copper, but stiffen it up by mixing zinc in to give it some structure. Heterogeneous mixtures are not uniformly mixed down to the molecular level. Like I said before, a pile of Legos. If you take a sample from over here and compare it with a sample over here, you're not going to get identical compositions. That is heterogeneous. So, a pile of dirt is heterogeneous. If I take a sample from over here and compare it with a sample from here, we're going to have different compositions. Same with blue cheese dressing. Take a sample from here and take a sample from here, and they're going to have different compositions. Same thing goes for a crowd of people. People are not identical. Therefore, any grouping of people will be, by definition, heterogeneous. Even muddy water is heterogeneous. And of course, my personal favorite, cat gork, cat vomit. When a cat when a cat meows at the carpet, if you were to take a sample from over here and compare it with a sample over here, this sample here might have a little more fur in it. This might have some like mouse bones, maybe some dry food up here. So it's got different composition throughout. Does this gross you out? So that's matter. Now let's take a look at the changes that matter undergoes. There are two basic kinds of changes. We have physical changes, which changes the appearance but not what the substance is actually made of. If you have the same substance before and after the reaction, then it's not a chemical reaction. It's actually just a physical change. For example, when you crush something, it's still made of the same stuff. It's just now has a higher surface area. Flattening. If you take something and you flatten it down into a foil, for example, then I can't show you that for copyright reasons. But if you take aluminum and flatten it down into an aluminum foil, that would be malleability. Dissolving. If you take something and dissolve it in water, you still have that substance because if you evaporate the water, you'll get the substance back. That's why sugar water tastes like sugar and salt water tastes like salt because the sugar and salt are still there. They're just mixed in with water. And if you evaporate away the water, then you're going to get your salt and sugar back. Melting. Melting is a phase change, and all phase changes are physical changes. When you melt, all you're doing is turning a substance from a solid, where the molecules are all packed together, into a liquid, where the molecules are further apart and free to flow. The molecules are made of the same stuff, so ice and liquid water is really the same substance, H2O. So if we take ice and we melt it, we still have molecules of H2O. You've just made the molecules a little further apart from each other. And of course, the same thing goes for freezing. When you freeze a liquid, you're just basically taking the molecules of liquid and arranging them in a nice crystal pattern, turning them into a solid. And of course, the same thing will go for boiling and condensing as well. Conducting electricity. When you pass electricity through a wire, well, it's still made of the same material. You haven't changed it. You've just passed electrons through it. Just like if you take a garden hose and pass water through it, well, it's still the same old garden hose. You've just let water pass through it. Stretching. If you take, like, for example, bubble gum and stretch it, well, it's still bubble gum. And we all that was going to be another video, but again, for copyright purposes, I can't show it to you. But if you ever watch the TV show Forged in Fire, where they take steel and they hammer it out into knives and stuff like that, that's a good That's a good handle on both ductility, the ability to stretch a metal out, and malleability, the ability to flatten it out. Now, on the other hand, chemical changes change what the substance is made of. So, for example, when you take a substance and burn it, the substance you end up with is not the same substance you started with. So, if you burn gasoline, when you're done, you don't have gasoline anymore. The atoms are still there, but they're now making up new substances. So, for example, when you burn gasoline, you take a compound made of carbon and hydrogen and react it with oxygen, and the carbon and the oxygen react together, and the hydrogen and the oxygen react together to make carbon dioxide and water vapor. So you no longer have the same substances that you started with. That makes it a chemical change. Rusting. Whenever a metal rusts, what happens is it's losing electrons to oxygen, forming a metal oxide. In the case of iron, iron forms iron oxide. Now, iron oxide is not iron. It is basically a compound made of iron and oxygen, and its properties are different. For example, iron can be attracted to a magnet, but iron oxide cannot be. So if that car undergoes a process of rusting, that would be a chemical change. Corroding. Corroding is another word for rusting. So different metals corrode or tarnish or rust. They're all words for reacting with oxygen. Synthesis. This is a reaction where two elements combine to make a compound. Sodium metal is heated until it melts and just begins to burn. So here we're taking sodium metal and we're heating it up, and then it's melting. And we take the molten sodium chloride and put it in pure chlorine gas, and the sodium and the chlorine begin to react very vigorously and violently with each other. We start to get white smoke given off, and that white smoke is actually microscopic particles of salt. So if we take this extremely reactive metal and this extremely corrosive gas and react them together, the substance we make, as you can see in that spoon, is just salt, sodium chloride. And since the substance we end up with is not the same substance we started with, that would be an example of a chemical change. Decomposition is another example. If you take a compound and break it apart into two elements, you no longer have the same substance. So if we take mercuric oxide, which contains both mercury and oxygen bonded together, and we add heat to it from an outside source, you'll see the color of the mercuric oxide is changing. But even beyond that, you're going to start to see a ring, a silvery ring appearing in the test tube. Keep watching. Silvery ring, oh where is that silvery ring? Right here, You're starting to see it building up on either side. That right there is pure mercury, and the oxygen has left the test tube. So we're decomposing mercury oxide into mercury and oxygen. And since the substances are different, it's a chemical change. By the way, we can test for the presence of oxygen by using what's called the glowing splint test. We'll see that in just a moment. A splint that is just glowing when placed into the oxygen will reignite. And that is a primary test. If you take a burning splint and put it in and the splint goes out, it's carbon dioxide. If you take a glowing splint and it catches fire, it's oxygen. And if you take either and it explodes, it's hydrogen. Flame tests. Very, very flaming splint test. Very, very handy. Any chemical reaction will generate heat. And that would be an example of a chemical change. So let's take a look at that. So right here we have some thermite, which is a mixture of two substances that I'm not going to tell. Oh, they tell you right here anyway. Aluminum powder and iron oxide powder. And once the reaction gets started, it's an incredibly violent reaction that produces aluminum oxide. And forming aluminum oxide generates a tremendous amount of heat, enough heat to melt its way right through sheet steel. The Mythbusters actually had an episode where they tried to cut a car in half using thermite. Fun stuff. That is a chemical reaction and therefore a chemical change. The law of conservation of mass states that you cannot create or destroy matter by physical or chemical change. You can only turn things into different things. So if we react 40 grams of substance A with 20 grams of substance B, that gives us a total of 60 grams of substance that we reacted. So if the only substance we form is C, substance C will have to have a mass of 60 grams because the mass reacted must equal the mass of what's formed. 60 grams. If we take 35 grams of liquid water and we evaporate it off, when we're done, how many grams of water vapor will we have? Well, you cannot create or destroy this mass. So if we have 35 grams of liquid water that entirely evaporate off, we're going to have 35 grams of water vapor when we're done. Magnesium metal reacts chemically with oxygen to form magnesium oxide. You'll notice we have two substances to start with and a completely different substance to end with. How will the mass of the magnesium oxide compare to the combined masses of the magnesium metal and oxygen that formed it? Well, the law of conservation of mass says they're going to have to be the same. Regardless of how much you started with, you're going to end up with exactly the same amount. You cannot create or destroy matter by physical or chemical change. Now, when we do the nuclear chemistry unit, I'll show you how you can create or destroy it using nuclear change, but not physical or chemical. And that, at long last, is the end of this presentation. I hope you found it informative and helpful, and I will see you next time.